So need to write. So the idea is if we have a graph here, when we say linear moles, by linear moles we mean um, functions of the form f of x. Specifically, when we write f of x equals mx plus b, right? You know that m here is called the slope and b is the intercept with the vertical axis. So that's what we mean by linear moles. And so if we had two ordered pairs, let's say that we have one ordered pair that has coordinates x1, y1, and another one that has coordinates x2, y2, then the slope is defined as a ratio, something typically we write as y2 minus y1 in the numerator, and then x2 minus x1 in the denominator. This is what we would denote with the letter m, and that's usually what we call the slope. So what we want to keep in mind here is that this it's also something that is measuring change, okay, and is measuring change in the independent variable, change in the dependent variable, right? So when we use this notation for functions, so it's common to assume that the y coordinate is the output of the function f of x. So this ratio is measuring like overall change in both variables, and this is actually called the rate of change. That's a very important quantification of what the slope is measuring. So let's say a little more about that thing. What is this rate of change? So if we say, look, so if we're measuring the number of cases, so if y1 and y2 are measurements of the number of COVID-19 cases, and this would be measurements in logarithmic scale. Okay, so if y1 and y2 are measurements of the number of cases, then when we consider the difference, y2 minus y1, this difference is telling us that this would be change, okay, in the number of cases. Now, this is in the number of cases, is really change in the log of the number of cases. That's really what that difference is. But you could think of it still as a transformation of the number of cases, and this is really telling you that this is measuring change. So if you're taking these measurements and counts that are daily counts, so when you normalize or multiply by 1/, so say when you divide by x1 minus x2, here, if the numerator are time steps of when the measurements are reported, and these are equidistant, so they are daily measurements, right? So that means from say day 3 to day 4, or day 5 to day 6, or something like that. So that difference between the day of the actual measurement, it's going to be equal to 1, and so we're going to have something like y1 minus, excuse me, y2 minus y1 divided by 1. So this whole thing is denoting the rate of change. Okay, the rate of change of, this is also called incidence, but rate of change of the number of cases. Okay, and so here we're saying that we are going to have a special case because the change in time units is going to happen to be 1. Okay, so we can then have scenarios here. This is M, so we can have scenarios. Maybe you should have an extra one. Yeah. Okay. So we could have what I was writing in the previous slide, that M, the slope, is the rate of change in the number of cases. This is of course in logarithmic scale, but and so here we can have scenarios in which M may be equal to 0, M may be less than 0, and M may be bigger than 0. So if the slope is 0, okay, so if the slope is 0, then in this case we would say, well, that means that there is no change. So if the rate of change is 0, it means that things are not changing. When cases are basically the same number and you're looking at differences in cases, if the y2 is the number of cases on a particular day and y1 is the number of cases in the previous time unit, in the previous day, and you take that difference to be 0, then that means that those two things are basically the same. So if it's close to 0 or close to 0, there's not actual change between the number of cases. Now, if the rate of change is negative, then here we would say that when that slope is negative, then we have a scenario that has negative rate of change. And that is the same as saying that negative rate of change, it means that the number of cases are in decline. So here we would see a decrease in the number of cases. So this is directly associated with a slope of a line that would look like that. Maybe it doesn't look too inclined there, but that's this is supposed to be, maybe I can draw this a little better. So this is supposed to be a line that kind of looks like that. Okay, and then the other case, if it's M is the slope is positive, then this would be a scenario in which there would be a positive rate of change, and this is analogous to have an increase in the number of cases. Okay, and in that case the slope has this shape. So you can see how because of how I'm drawing this slope with that arrow there, the arrow there at that end, that arrow is kind of pointing upward, and the other scenario there with negative slope, the arrow is pointing downward, but this is there upward and downward in some specific sense of direction. Okay, so positive slope means positive rate of change, which implies an increment or increase. Remember, these are consecutive measurements over consecutive time units, and negative rate of change implies a decrease over consecutive time units, right? So let's consider a scenario that looks kind of like this. So here on the horizontal axis, we have time measured in days, okay? And then the vertical axis, we have the number of cases, but these are cases in logarithmic scale. So still, I've not specified if that log is base 10 or base E, okay? That matters, but in terms of, matters to be specific, but in terms of the general trends, it should not matter for your analysis. So you simply have to report which base are you using, if it's base E or base 10, okay? But let's suppose that this is a representation of the data. So here we would associate immediately each of these lines would be associated with some slopes that I'm going to call here. This would be m sub 1, this would be m sub 2, and this would be called n sub 3. And each of those slopes is positive. So you can see clearly that all these slopes, as they are the slopes of those lines, each of these lines being a segment or a piece, right? I still have not said what is exactly the equation of that line, but I'm just giving you making some comments as to the possible shapes of these lines. So even though we expect all these three slopes to be positive, all of them measuring positive rate of change, their positivity, they're positive numbers, but these numbers do have differences, okay, substantial differences between each other. So this would be a time when I would, let me see, I would switch. What do I do first? I want to switch over Desmos. There is this other scenario. Okay, so let me just annotate this, and then we switch to Desmos. So this is another scenario, three slopes associated here. So here's M1, M2, and M3. All these slopes are positive, okay, but these are very different positive numbers. So in the previous case, the first line has a slope value that is considered this to be a slow beginning or initial phase, because this initial slope, okay, even though it's positive, is smaller than the other two slopes, than M2 and M3, okay? So in the other case, the very initial slope M1 is the largest of the three positive numbers. So in this case, this value of M1 is bigger than M2, and M1 is also a lot bigger than M3, okay? So in fact, considering only 3 time windows here, that is the subdomain where the slope has its largest value. And now the other scenario is one of the following picture here. So we have M1 for the first slope, M2 for the second, M3 for the third, and then there's a fourth subdomain for region here, which I'm going to call N4. So very importantly, what you see here is that M1 is positive, M3 is also positive, and so is M4. So these three slopes are positive. However, M sub 2 is a negative slope. So what we're seeing here is that, again, if we're measuring days in the horizontal axis and then cases or log of cases in the vertical axis, then it is rewarding to see that there are some values here. Okay, so I'm gonna call this is maybe t equal 1, and then I'm gonna call this, I don't know, t2, and this would be t sub 3. So there is an interval between t sub 2 and t sub 3. This is an interval, okay, a time interval where the number of cases was going down, was decaying, okay? And so that's exactly the kind of thing that we'd like to see right now with the COVID-19 pandemic. We'd like to see either scenarios of something similar to M3, or hopefully something like M2 with negative slope, because negative slope means that the number of cases are going down. M3 is not bad. Is actually M3, as is depicted here, M3 should really be almost 0. So M3 is one of those similar, not exactly the same, but is similar to that scenario of having little to no change. So having a rate of change that is almost 0, it means that would also be another good thing to see.